So welcome everyone. So in this unit, we're going to find out the input-output relationship when the diode is on and when the diode is off. So we found out in the previous unit that after drawing the transition state line, which is Vi is equal to 1.4, we have T1 instant when Vi is equal to 1.4 occurs. We have T2 instant when Vi is equal to 1.4 occurs. And we found out any value or the range of voltage above this dotted line or above this Vi is equal to 1.4 line, the diode is on. And the range of input signal below this Vi is equal to 1.4 line, diode is off. So this line gives us the boundary between on state of the diode and the off state of the diode. So now we are going to draw the input-output relationship when the diode is on and when the diode is off. So first of all, let's do it for off. So when the diode is off, let's redraw the circuit. So D2 off, then the resistor, D3 off, the resistor, Vi, which is R, and V0 is the voltage. So since the current is 0, V0 is equal to 0. So during this interval, we find V0 is equal to 0. Also in this interval, when the diode is off, V0 is equal to 0. So let's see what happens when the diode is on. That means during this interval, on interval. So let's redraw the circuit, considering the diode is on. Plus, minus, Vi, plus, minus, plus, minus, and this is R, so V0, plus, minus. So if we apply KVL, this is the plus minus, the polarity is like that. So from this is our D2, so D3, so that should be our positive terminal of the voltage. This is negative. So that is our reference point. So you have to remember this is our reference point. Let's say this is our ground reference point. So voltage is measured with respect to this point, the reference point. If I apply KVL, that we get Vi minus 0.7 minus V0 minus 0.7 equals to 0. So that gives us V0 is equal to Vi minus 1.4. So that is the input-output relationship when the diode is on. V0 is equal to Vi minus 1.4. So this is how we obtained the input-output relationship when the diode is on and when the diode is off. So if we try to draw the input-output relationship for positive half cycle, so we're going from 0 to T1, V0 is equal to 0. So that means 0 to T1, we can draw the V0 is equal to 0. Again, T2 to T by 2, V0 is equal to 0. From T2 to T by 2, V0 is equal to 0. V0 is equal to 0. Now we need to draw between T1 and T2. And between T1 and T2, V0 is equal to Vi minus 1.4. So we already learned V0 is equal to Vi means output is going to take the same shape as input. So that means we're going to copy the shape of input and then paste it as output. Except that we're going to drop it by 1.4. So how can we obtain these points? So one way you can obtain this point, if I set 3 terminal points, T1, T2, and max. So at T is equal to T1 and T2, we know that Vi equals to 1.4. So if you plug the value of Vi for T1 is equal to T1, for T is equal to T1 and T2, we got V0 is equal to 1.4 minus 1.4 equals to 0. So that gives us 1 point, another point, and 0. And then at maximum, at Vi max, which is our Vm. So V0 max would be Vm minus 1.4. So that means at this instant, at that voltage, output would be minus 1.4. So if I, now we know that the shape will remain the same. So we can draw it like this. It could have been nicer. So that is our Vm minus 1.4. So that is the output shape. You see, from 0 to T1, since the diode is off, there is no current flowing through the resistor, so the output voltage is 0. T1 to T2, since the diode is on, current is flowing through the diodes and through the resistor, so we have a voltage drop, which is obtained using this relationship. So that means input and output has the same shape, except that the output will be dropped by 1.4. So that is what happens in our positive half cycle. So next, let's see what happens in negative half cycle. So once the positive half cycle is over, we are done with positive half cycle, then we have the negative half cycle, which happens T is greater than T by 2 T, which is Vi less than 0, negative half cycle. So when it's negative half cycle, what are we going to do? We're going to change the polarity. Okay. Polarity is changed. Same as before, if you have a single voltage source and multiple diodes, in that case, any diode that appears to be reverse biased will be reverse bias. So this way we find out D2, P side of the D2 is connected to the negative terminal and the N side of D2 is connected to the positive terminal. Similarly, D3, P side of it is connected to the negative terminal, N side of it is connected to the positive terminal. So this way, this diode and these diodes are out. However, D1 and D4 appears to be forward biased. So this way you have managed to reduce the numbers of diodes. So again, we're going to determine the transition state voltage. So for that, we need to draw the circuit first. So let's redraw the circuit. Okay. So that is our D4, D3. So plus, minus, Vi. So at transition, we're going to replace the diodes with 0.7. So let's say the current is flowing. Let's assume the current is flowing in this direction, I, plus minus I. So if I apply KVL, plus to minus VI plus 0.7 minus IR plus 0.7 equals to 0. So I being 0 at transition state, so we get VI is equal to 1.4. Now be careful about this one. So we got VI is equal to 1.4. So we obtain a VI positive value. But notice that we already consider VI to be negative. So that means we know for which reason we are talking about. So we are talking about negative half cycle. So that means if you obtain a positive value of 1.4, it only applies for this negative half cycle. So it doesn't apply. Positive value doesn't mean that we have to draw it in for positive value of VI. It means we know plus minus means we already know we are in negative half cycle. Already defined it. So then what we obtain is only the value. So that means we are going to draw the line here. So next step would be drawing the line. We draw the line. So let's say transition state line. Again, we know the transition state line. So it gives us the information about the boundary between the on state and the off state of the diode. And since the diode D1 and D4 appears to be in anti-clockwise direction, if you keep our signal source to the left, you see anti-clockwise orientation, okay. So this is the orientation of the diode. So in that case, we know that below the diode is on. For the range of voltage below the transition state line, diode is on, and the range of voltage above the off. We have off state there and on state. So we found out the range, the boundary at which transition between on and off occurs. And then, so this line intersects the signal here and here. So the time corresponding to this value is T3 and the time corresponding to this value is T4. So mathematically we can write, first of all, VI greater than equal to minus 1.4. So any value above this line. So minus 1.4, greater than minus 1.4, this value, diode is off. On the other hand, VI less than minus 1.4 on. So that means this is minus 1.4 line. So any more negative value, so this value, this value, this value, this value, this value, for this voltage diode is on. So let's find out the time interval. T is greater than T by 2 less than T3, which is VI greater than equal to minus 1.4 off. So between T3 and T4, so VI is less than minus 1.4 on, and between T4 and capital T, off. So we know when the diode is when the diode is off, the time interval when the diode is off, and the time interval when the diode is on.